Chapter 7b, The Origins of Quantum Mechanics. In the late 19th century, science progressed significantly. For example, scientists already knew that atoms were basic constituents of matter. Newton's laws were widely used to describe the universe. Scientists believed that we had already enough theories. The only thing to improve is accuracy. However, later, several experiments proved to be difficult to explain using classical physics, and it was these experiments led to the discovery of quantum mechanics. And this includes blackbody radiation, photoelectric effect, heat capacity, and atomic emission spectroscopy. Any object emits energy because of the thermal motion of its molecule. The radiation emitted goes from a low frequency, which is red color, to a higher frequency, which is blue color, as the temperature increases. For example, if you heat your stove, you may see the color goes from red to blue, depends on the temperature. A blackbody is a system that absorbs and emits all frequency and serves as idealization for any radiating material. Scientists try to correlate the emitted frequency to the temperature of the body. However, they failed to use classic physics. Here shows the experimental data, the emitted radiation intensity as a function of wavelength. And you can see there's a wavelength at which the intensity is a maximum. The maximum wavelength decreases with temperature. And there's a mathematical equation formulated by Wien called Wien's law, says that the product of the wavelength, maximum wavelength, times temperature equals 2.9 times 10 to the minus 3 meter Kelvin. Again, this comes from experiments with a maximum wavelength. By using classical physics, scientists formulated the equation, and plotting this equation gives you this curve which matches experimental data at a high wavelength, but deviate significantly at low wavelength. In fact, at low wavelength, experiments show there's a maximum, but theory suggests it goes to infinity. Now, low wavelength means high frequency, which is in the UV range, and scientists call this UV catastrophe. In order to explain the experimental data, a scientist called Max Planck proposed that energies of light-generating oscillations are quantized. Energy radiated by oscillators is proportional to the frequency, as shown in this equation. So n is the integer, which can be 1, 2, 3, okay, any integer. And h is a constant to be determined. And v is the frequency of oscillator. Based on this equation, he formulated an equation of the intensity of the radiation as a function of temperature. This equation gives a plot that matches experimental data perfectly. And then using the experimental data, Planck found the constant h to be 6.626 times 10 to the minus 34 joule seconds. And this is nowadays called the Planck constant. Note that Planck postulated the energy quantization simply to match the experimental data. Even him didn't believe this should be the theory. And he thought that in the future there may be a better theory to explain the data. Many of you did the flame test in general chemistry. Elements, when heated, give distinct color. For example, lithium give you red color, sodium give orange color. Hydrogen gas, when heated, it also emits light with only certain wavelengths. These include 410 nanometer, 434 nanometer, 486, 656. Okay, scientists wonder why it only emits this wavelength instead of continuous. Why not 410, 11, 412, 413? Classical physics offers no clue. A mathematician, Johannes Rydberg, formulated the mathematical equation to simulate these wavelengths. And in this equation, RH is a constant called Rydberg constant, is this number, and f and I are two integers. The only requirement is I is greater than f. For example, f can be 2, I can be 3, or f can be 3, I can be 5. Okay, using this equation, you can find all these wavelengths emitted by hydrogen gas. The question is what are these integers? What do they mean? Nobody understood when this equation was formulated. If a hydrogen atom emits light with only certain wavelengths, then the energy of the hydrogen atom itself may be quantized. And based on this observation, Niels Bohr proposed a model to explain atomic structure. There exist stationary electron orbits. The orbitals have specific or quantized angular momentum and energies. And the electrons can jump between allowed orbitals. The energy difference is the photon energy, which is proportional to the frequency. So based on this model, we can explain why hydrogen only emits certain wavelength. And this is because when the electron goes from a higher energy level, for example, N2 to N1, and that will emit a light with the first, let's say, this wavelength. And if it goes from N3 to N1, that gives you a different wavelength, and so on. Now, based on the model, Niels Bohr calculated the first orbital radius to be 52.9 pm. Pm means 10 to the negative 12 meter. Okay, and this radius has a symbol A0 called Bohr's radius. Based on Bohr's model, the energy of an electron is determined by the number of orbitals. N equals 1 is the first orbital, N equals 2 is the second orbital. Suppose electrons jump between two energy levels from Ni initial to Nf. The difference, delta E, between these two energy levels can be calculated. And this equals a photon that emitted, HV, and therefore we can calculate the frequency of light that is emitted, which is determined by the two energy levels, Nf and I. Compare with Rydberg equation, we can see that all these constants combined together is Rydberg constant, and the two integers in this Rydberg's equation are simply the number of orbitals of the electrons. Bohr's model was a great success and explained the hydrogen atom spectrum and the origin of the Rydberg formula. However, it failed when applied to the spectra of other atoms. A new theory is needed. Example: atomic sodium produces a yellow glow resulting from the emission of radiation of 590 nanometer. What is the energy transition in kilojoule per mole that is responsible for this emission? So in sodium atom, the electrons have different orbitals. So the transition between two orbital energy level is responsible for an emission of the radiation. And the delta E, this transition equals to the energy of the light that is emitted, and the energy of light of this wavelength is calculated by Planck constant times frequency. Now, if we have wavelength, then we use the speed of light divided by wavelength. That gives you the frequency. So plug in the data, Planck constant, speed of light, wavelength, from nanometer change to meter, 10 to the negative 9. And that gives you 3.37 times 10 to the minus 19 joule. Example 2. Calculate the number of photons emitted by 100-watt yellow lamp in 1 second. Take the wavelength of yellow light as 560 nanometer and assume 100% efficiency. The energy of one photon should equals to Planck constant times frequency. And if you have n number of photons, the total energy should equals to n times hv. And therefore n can be calculated by total energy divided by Planck constant times frequency. Watt means joule per second. So in order to know total energy, you need to times time. In this case, is 1 second. And therefore, you use power, which is 100 watts, times 1 second in this case, divided by Planck constant times frequency. So frequency can be calculated by speed of light divided by wavelength. So plug in all the data. It gives you 2.8 times 10 to the 20 seconds, 20 power photons. We discussed the blackbody radiation and atomic line spectrum. And now let's look at another experiment, photoelectric effect. When you shine lights onto a surface of a metal, some electrons will be knocked out of the surface. So this is called photoelectric. Photo comes in, light goes out, or electron goes out. Scientists try to find the relation between the kinetic energy of the electron and the frequency of the light. Classical physics failed again in this experiment. According to classical physics, light is a wave, and the energy of wave is determined by amplitude, not frequency. Suppose we have two water waves. One have a high amplitude, the other has a small amplitude but large frequency. It is the first one that has higher energy. Okay? And therefore, a bright, intense light, which has a large amplitude, should have high energy, which can knock electrons out of the surface with high kinetic energy. Compare red light and the blue light. They have different frequency, but even for red light, which has a small frequency, as long as it's bright and intense, it should have high energy and knock electron out, give high kinetic energy. Experimental results were different from what the theory predicted. The kinetic energy of ejected electrons depends on the frequency, not the intensity or the brightness. When the frequency is too low, nothing comes out of the surface. Only after this particular frequency, electrons start to come out. And this frequency is called threshold frequency. Different metals have different threshold frequency. After threshold frequency, the kinetic energy of ejected electrons is proportional to the frequency of the light. Brighter or more intense light eject more electrons, but the kinetic energy of electrons are not changed. Photoelectric effect suggested that wave property alone cannot explain the results. Light may behave also as particles. Einstein postulated that light comes in discrete package called photons. The energy of photon is proportional to the frequency, and each photon has an energy a constant times frequency. By fitting the data, he found out that the constant is 6 times 6 26 times 10 to the minus 34. And this is exactly same as the constant Planck found. So two different experiments give you the same constant. And that indicates the importance of this constant and the importance of the concept of energy quantization. The kinetic energy of ejected electron can be calculated using energy conservation. One photon comes onto the surface, and the energy is h times v, frequency. And this energy is absorbed by an electron. The electron uses this energy to overcome the binding energy. Electron is bounded to the surface, so in order to escape from the surface, it has to overcome this energy first. And the actual energy becomes the kinetic energy of the electron. If the incoming light has energy smaller than binding energy, then electron cannot escape. If the energy of one photon equals the binding energy, then the electron can escape with zero kinetic energy, and this frequency is the threshold frequency. Example: the threshold frequency of barium is 6.07 times 10 to the 14 Hz. What wavelength of light is needed for the barium surface to emit electrons with kinetic energy 1.31 times 10 to the negative 18 joule? According to the energy conservation, the HV equals binding energy plus kinetic energy. In this question, kinetic energy is given. It asks you what is the wavelength. So if we can calculate the frequency first, then we can calculate the wavelength. But first, we need to know the binding energy. And the question tells us the threshold frequency. So from threshold frequency, we can calculate the binding energy, which equals Planck constant times threshold frequency. Plug in the data, the binding energy can be calculated. And then plug in this equation, we can calculate the frequency, and then the wavelength should use speed of light divided by frequency. That gives you the wavelength. Young's double-slit experiment showed that light has diffraction pattern, and therefore it's a wave. But the photoelectric effect showed that light is composed of particles or photons, and therefore it is a particle-like behavior. So light behaves both a particle and a wave, and it's called wave-particle duality. A young scientist called de Broglie thought that if light can display wave-particle duality, then the particles such as electrons, protons, neutrons may also display wave properties. De Broglie also formulated the mathematical equation to relate these wave and particle properties. Wavelength equals Planck constant divided by momentum. Momentum belongs to particle property, and lambda wavelength belongs to wave property. 3 years after de Broglie's postulate, a number of experiments confirmed the postulate. For example, an electron beam was projected onto a surface of a crystalline solid. Diffraction pattern was observed, and the interference pattern was characteristic of de Broglie wavelength, defined by this equation. According to this de Broglie wavelength equation, momentum and wavelength are inversely proportional. A short wavelength implies a high momentum, and a long wavelength implies low momentum. Let's compare wavelength of an electron with that of a rock. To calculate wavelength, we use de Broglie equation, Planck constant divided by momentum, and the momentum is calculated by mass times velocity. For electron, the mass is 9.11 times 10 to the negative 31 kilogram, and the speed here is given, all right, is 1 times 10 to the 7th power meter per second. So the wavelength is a small number, 7 times 10 to the negative 11. Although it's a small number, it is comparable to the size of an electron. All right, because the size, small size, so the wavelength comparable to its size, and therefore wavelength is important. The wave property is important for an electron. So when we talk about electrons, we cannot ignore the wave properties. Now let's calculate the wavelength of a rock. Same equation. In this case, the mass is 50 gram, so times 10 to the minus 3 kilogram, and the speed 40 meter per second, and that gives you an even smaller number, 10 to the negative 34. And this is so small. And think about the size of a rock. A rock is probably centimeter or millimeter. And so because the wavelength is much smaller than the size of the rock itself, the wave property is negligible. It's impossible to see the diffraction interference with such a small wavelength when the size of the rock itself is large. So these two calculations shows that wave properties is important for at the microscopic level, but not important for a macroscopic level. In this section, we learned that in classical physics, wave particles are distinct entities. Waves are characterized by amplitude, wavelength, and period, and wave propagation is governed by wave equation. Particles are characterized by mass and velocity. Particle motion is governed by force and Newton's equation. In quantum mechanics, matter appears as wave-particle duality, and the wave particles properties are related by the Broglie wavelength equation. Now this equation is important, but it's not enough. Is there an equation in quantum mechanics just like Newton's equation in classical physics? And that's what we are going to talk about in the next section. Summary. In this section, we showed that there were several experiments that classical physics failed to explain, and these experiments led to the discovery of quantum mechanics. Blackbody radiation showed that energy of light is quantized. Atomic emission spectroscopy showed that the energy of electrons in an atom or molecules are quantized. Photoelectric effect shows that light has wave-particle duality. De Broglie postulate that all matter has wave property, wave-particle duality.